Dheeraj has already introduced myself, Karan Banthia. I'm working as a software engineer. Today's talk is going to be on design patterns, not in the Gang of Four book ways, in a generic way. We use the same concepts. The concepts are not going to change. The implementation are going to change. So let's get started on that. So first, the talk contents would be an intro on generic programming. So generally, we follow OOPS-based approach where we try to model the real world in base classes, virtual functions, abstract classes, and all that kind of stuff. Then we create a model, and then we uh, create implementations, extend it, inherit it, and do a lot of stuff. So generic programming does away with almost all of it. There are still objects, but we'll see what generic programming is and why do we need it. Then as one by one, we'll start talking on some design patterns. Abstract factory is the most popular, actually, the factory pattern. Then alternative to pure virtual base class, that is the abstract class. Why do we want it? Why do we not want it? CRTP, template method, type eraser, strategy, and bridge. All these are design patterns. We'll go through them one by one. Again, the concept still remains the same, be it C++11 or be it C++20. The implementation will differ and the uh, gap, the distinction between the design patterns will be very minor. So we have to identify what it is that we need. So we'll go one by one. And the takeaway from this session, what I expect is how to combine and or link design patterns should be an understanding. What design pattern to use, when to use, where to use, that is all fine. But when it comes to how to use it, everything else blurs out. So how is the most important question in design patterns? Otherwise, theory-wise, it's all fine. So let's try to understand how. Probably in this examples, in this session, whatever examples I'm going to present, you might be able to use it directly, but you probably won't because it is an approach. It is how and not uh, directly the implementation of it. So we'll go. Now to give a background, the environment we are using is a microcontroller or a microprocessor. So when I say microprocessor, maybe around 500 megahertz, 1 gigahertz, with not a lot of RAM, say external GBs of RAM or not Linux running on it. You can use the same concept on Linux. Any other thing, you can use the same concept in a desktop environment where it is not microcontroller, that is fine. But the target will be this. Compilers, usually embedded systems run today at C++11 or 14. Some will have C++17, but C++20 is the way to go ahead. There is no reason not to jump directly from 11 to 20 and to go from 11, 14, 17, and then 20. Probably start with 20. We'll see why. Then I'm running on FreeRTOS instead of Linux. And templates, we will be using templates quite a bit. And using templates will increase compilation time in general. But if it is a huge code base, it matters. If it is not a huge code base, the compilation time would be like a minute or 2 minutes or 5 or 10 minutes, not in hours. So that is acceptable. That is an assumption. So if your code base is very huge, would take 5 hours to compile, then you need to rethink on templates. There are some optimizations, but yeah. So the setup we have is, suppose we have three tasks, three independent tasks running in a microcontroller where we have a console. Console can be, say, over a UART. It can be it can be to a host computer or it can be through a master device. So suppose we are running a slave device, any of it, or it can be over a network. So over a network, you get something and it reaches your console. There is a logging task. The logging task, these are all pre-RTOS tasks, by the way. So a logging task will either log to the console or it can log to a file system. So we'll keep it only two options for now. So file system would mean an external memory where we have a crude file system, not like a Windows or Linux file system. So it's something you can log. And we have an application which can be a user interface. So for us, let us keep simple. It is a blinky LED, one or two or three LEDs, whatever. It can be a graphics display or anything. So we need a user interface. We need a background task, which is a login task, and we need a interface like the console. So three tasks is our setup. That's it. Now, what is generic programming? Now, why do we not want OOPS? So, generic programming, in the famous book of modern C++ designed by Andre, he has mentioned that it is a paradigm that focuses on abstracting types to a narrow collection of functional requirements. So, that is basically functions, in short, and implementing algorithms in terms of these requirements. So, again, it is functions. So, what it says that you should have a set of functions which take in data and give out, process the data and give out the results. Don't bother about anything else. So functional requirements, and those functions are providing service on the data that you have. In embedded, all you have is data. So in this case, we still model a solution. Okay, we still have objects, we model a solution, but independent of underlying data type. We don't care whether the console is uh, a 8-bit, a byte console or 16-bit or something like that. It doesn't matter. We'll make it generic and we'll make it to provide service on whatever the data is. The type can be different. So it still involves designing objects. It's not just like we have a couple of functions with template parameters and we use those functions directly. Yes, you can do that, but we still have functions inside objects, but those objects are not inherited related in an inheritance hierarchy. So you don't want to create an entire jungle out of it. So somewhere I read that suppose in C++ I want to create a banana. So if I go to the oops approach, I will get a gorilla holding a banana and the entire jungle because we try to model everything. We don't want to do that. All I want is a banana. That's it. So there's a very nice talk on data-oriented design by Mike Acton. So please try to refer this. He explains in detail why don't we want to model our system in terms of real world. All we want to focus on is data. That's it. In, data in, process, data out as a service. That is generic programming in simple terms. So what does it give us? And when does it help us? So why are we doing this compile time or generic programming? Because we want to debug our system less. Why would we want to do that? Because we want to be more efficient on the design aspect. So one of the approaches is avoid null pointers, avoid void pointers, avoid reinterpret cast, doing something at runtime which you can already do at compile time. Registering callbacks, registering components, one component to another. All these bindings you can easily do at compile time in most of the cases. If this information is not available at compile time, then generic programming might not be able to help. But it can still help you. Suppose what would be the scenarios if your application is dependent on some either another binary or some other master device so that you get the information only after that binary is up or the device is up, or you want to read it from the file system, or the input is received in some way at runtime, or if it is a read before write kind of situation, so it is a memory allocation. So there you have to allocate memory. So reading to an external memory, those kind of things. There you cannot 100% do compile time programming, but here it can still provide you type safety because in these cases, generally you have a null pointer somewhere or a void pointer which is initialized and then it is assigned some value after you receive the information. So it is not type safe and then you're interpreting the type on top of it after it is assigned. So you can use type safety even in these circumstances. So this is about compile time programming. It is a very brief overview as such. It will get clear, things will get clear as we go into the design patterns aspect of it. Now say this is the first and the foremost most important common abstract factory design pattern. So all these codes and the definition is taken from the Gangs of Four books. So provide an interface for creating families of related or dependent objects without specifying their concrete classes. In our example, we have a logging system or logging task. So the logger on the left side, if you can see, the logger will have a read write operation on memory or console somewhere. So if you want a message, you can prepend a message, you can add something to that message to send it on the log or to the file system. You want to append it, you want to compress the message or encrypt the message if you're logging to an external memory. This is optional when you want to do it on a console. You don't want to compress and encrypt. So what do you do as per if you want to create a logger object? What do you do as per the factory pattern? You create independent these objects on the heap and then you link them together. So you provide a factory which is just an interface for creating these objects. It is not doing anything else. So it is a logger factory and oh, there's two times public. Okay, so it will make a logger. So this is the first object it will create. Then it will create pre-formatter, which is prepend message. It will create a post formatter. Now this is common. This is shared across all types of loggers. Now if I want a file logger, I can inherit from this and I can create two more. I can add to it a compressor and an encryptor. So these are two more objects which get created. And how do I use this factory? I would need an object of this in reference. Suppose in the logging task, I want to create a logger and I want to pass this factory. So I can have two types of factories here. I can have either the logger factory base or I can have the file logger factory, depending on what do I want to instantiate. And this will only call the factory methods. So in this, all these methods are called make logger, make preformatter. All these are called factory methods. And this is an abstract factory, which is a collection of factory methods. So I will call these factory methods and I will create these objects and I will keep a reference, a pointer to these objects in the logging task. And then after this creation is done, I can link this together. So I can link the logger to a prepend, logger to append, and I can initialize this, read, write, all this on this. But the point is, why are we creating all these objects on the heap? Among this, what is the information which you don't have at compile time? If you have this information at compile time, why use a factory? Probably you're never in an embedded system, probably you're never going to destroy it. So if there is a scenario where you want to create an object, use it and destroy it, then again create next. Probably in those cases, you would need factory, but in most of the cases, not required. So always try to avoid using factory or builder or creation on the heap as much as possible. There will always be an alternative in most of the cases. Say some standard alternatives which C++ provides. These are standards. We are not even considering design patterns or adding classes or interfaces on top of it. So std move, so or a move semantics, R value reference. So the constructor itself can take an R value reference and you can pass an object while creating in the constructor itself. So you can use a lambda for creating it, or you can use a placement new. We'll see what placement new is, and you can pass it directly here. Or if you want, you can pass the type as a template parameter and then the object in the constructor. Even that is possible. So these are standards without using design patterns. Or if you don't want pointers, so pointers you can assign it to null. So this I can assign it to null and then make use of it. So while testing or creating unit tests, someone can misuse it, assign it to null pointer. We don't want it. If the logger is a null pointer, if the prepend is a null pointer, would my system work? If the answer is no, then it should never be a null pointer. So probably it should be a reference. And if it is a reference, and if I create the object first and don't assign it a value, it will give an error. So probably you try to use std vector with a reference wrapper base class. So it will give you an empty vector of references to some object, and then you can create it. This is an alternative. This is not something which might go into production because reference, you need to be very careful with vector. It is a dynamic object, but it is an alternative which you can use. So any questions till now on the generic programming or the abstract factory? So this is till now OOPS based approach. So any questions till now on here? We are moving ahead into generic programming after this.
So if you have any question, you can unmute yourself and you can ask.
Okay, if not, please ping in the chat window. We'll take up questions in the middle. And I'll stop at one or two more points before we take questions at the end, all of it. So
Karan, here is one question. Someone asked, why not to use smart pointers?
smart pointers, are you ever going to destruct it? See, yes, unique pointers is there. You can use unique pointer, never destruct it. But it increases the size. Shared pointers specifically. Yes, you can use your unique pointer. And that is not the point here. So in production code, I would preferably, instead of rod pointer, I would use unique pointer, yes. But sometimes in a constrained environment, you don't even want the overhead of a unique pointer. So yes, you can use it, but not all the time, specifically if it is on the heap. Did that answer the question?
Hey, Daya here. Just a bit of a follow-up as about what you just said about unique pointer adding a bit of overhead. I'm not from an embedded background. I mean, I mostly do user applications on Linux, so unique pointer is kind of a bread and butter for me.
Yes.
But how much? I mean, has there been any profiling done based on which you're saying that unique pointer is not like a zero cost abstraction, or what kind of a cost is involved on embedded systems? Just curious.
Yeah, so in terms of code size and in terms of indirection. So I have not done extensive profiling on all the unique pointers or usage in my code base, but depending on, even if it is one or two indirections more, so because it will hold a pointer and it is an object. So it increases latency when it comes to interrupts, specifically interrupts. So there is not much profiling information that I can share with you or I have as of now, but we use less unique pointers. That's what I can tell you.
Yep, thanks for that.
Okay, so now we saw a base class which was not abstract, but we have abstract base classes all the time so that we can uh, force the derived class or the implementation to implement the pure virtual methods. So suppose I have an SPI, so I want it to be a read-write peripheral. So read-write peripheral should have a send and receive function. So I would rather create a base class, abstract base class, have a send receive, and let the SPI or UART or I2C, anyone, make it implemented. Again, this leads to vtables and virtual dispatch, and we don't want it. So one good alternative is type traits. Uh, I'm not going into type traits here in 14 and 17 because the syntax becomes too big. But C++ 20 will have constraints, which is again a named type trait. So this can be a very good replacement for an abstract base class. So I have a concept which can be called as read-write peripheral. So read-write peripheral like, and I want any object, whichever is passed to some function, to have a send function and a receive function. So the SPI, so if I'm using a console, and for the console, I need a peripheral. So instead of giving a base class reference, I would directly pass the type as a template parameter and say that this type should be like this concept. So this type by default will have to implement send and receive functions, a send function which takes a uint8 pointer and a receive function which takes a uint32 reference. So source and this. If it doesn't do that and it returns a bool, so this is returning a bool. So this function definition, instead of pure virtual function in the base class, it became a constraint in a concept. If I don't do this, if I don't implement send and receive in SPI or whichever peripheral I pass, it will fail at compile time. And there is zero overhead at runtime dispatch. There is no virtual functions. So this you can avoid virtual base classes or abstract base classes using concepts to a really good extent. So if we are using CRTP, then it doesn't work quite well easily. You'll have to get around it some way. But in most of the cases, if I want to constrain a class for which I'm passing a type, and I want to constrain the type to be like to behave or contain some specific functions or types. So the constraints can be over type as well. So you can have using type name as this. You can have all those. There are different kinds of constraints. We won't be going into all the constraints here. It's an independent topic. So you can constrain a class, a template parameter, and you can constrain a function template parameter as well. Same goes for the function as well. So in my console, I'm not referring to any base class. I'm directly referring to the derived class, which is the implementation. It can be SPI 1, 2, something. And this should have a send and receive function by default. That's it. And when I use it, I will create an SPI object, say SPI2. And for the console, I will pass this SPI and I will pass the object here itself. And I'm storing a reference. I'm not creating the object inside. So I'm storing a reference to this object without any base class overrides. Another approach, if you want to use runtime allocation, is to use the placement new or construct at. Construct at is just placement new uh, C++20, or you can say API, STL API over placement new. So small buffer optimization will say that I want to calculate the memory of an object, and then I will have an array of that size on my stack inside the object. Once I have that, it is an array of uint8 always. Once I have that, I can construct the object of that size at any time in the program lifecycle. So it is still using new, but placement new. And I can constrain this requirement as well. So whatever I pass, so suppose we'll go to this concept later. Suppose I have a function mem size cal and I pass it different types. and I can return the combined size of all the types. So if I have a header and a packet and packet 2, something like this, three kind of types. So I can pass three types to it, and it will return me the size of all three types. So it is equivalent of saying size of type 1 plus size of type 2 plus size of type 3. All we have done is creating a lambda function out of it, because we can reuse it. If this is in a header file, I can reuse memsize calc by passing any number of type parameters to it, and it will return me the size of the combined size of all the types. And once I have that, I can invoke this in an std array. I want an std array of uint 8, and I can invoke this operator in the template parameter itself. So it is all done at compile time, and I can get an std array of this received message size, of this size, which I named it as receive message. And while using the received message, I will use a placement new either. So the placement new will need a buffer. So the buffer is received message dot data. This is the starting location. The type of the object which I want to create, which is message header, and the parameters to it. So you can construct an object at this place using placement new. And since we have this message, see again, whichever for the mem size calculation, whichever template parameters I'm passing, I'm restricting it, I'm constricting it to be constructible. So if it is a non-constructible object, then it will again throw a compile time error. So you can add more constraints on this type. You can have different types of lambdas in your header, and you can pass it. So it is completely type safe at compile time, and you can create those objects at runtime. Deleting those memory is a task. If you want to reuse it, deleting or deallocating it is really a task, because in some cases you can run the destructor. uh, you'll have to write a specific destructor to it to deallocate it. In some cases, you will have to go and manually write 0 to those locations before you reuse it. But there is probably not much reason to destroy anything once you construct at runtime in an embedded environment. So this is sometimes called as local buffer optimization as well, because this buffer is local to a class. And the way you access it is provide an API with reinterpret cast. Yes, again, this reinterpret cast will again increase overheads because it is interpreting at runtime, but there is not much choice here. The only thing good about is that it is inside a function as an API, so that the developer need not write reinterpret cast or use a different type by mistake while interpreting a pointer. So that safety you can assume, and it can return a constant to a pointer instead of pointer. It can return a constant to a pointer, and it will be somewhat safe, I can say, not 100% safe, but better than using new on heap.
Question here. Can you please go
Yes,
back?
yes.
Why can't we use immediately invocable lambda here? Do we
Yes,
specifically have to call operator or parenthesis operator?
because we have a template, right? Since
Yeah,
we have
but
a
still we can make a mem size calc as a immediately invocable lambda, and
yes,
then we don't even have to use call operator dot operator, and then we can instantiate as a with a curly braces and then pass in template object, right? Template types.
yes, yes, yes,
And also
definitely.
one more, we can also make use of here in the array construction. We can also make use of class template argument reduction, right?
Yes, that I have not done specifically, because memcalc size, see, this is a very simple way of doing it. Uh, in production, it won't be as simple. There will be multiple types. I don't expect only single type to be there. So there will be multiple types. So it would be the actual implementation would be a meta program, I would say, a meta function. So for simplicity, I've kept it like this.
Okay. Can you please go back in the previous console creation? At that time, we can make use of CATD, right? Console instantiation.
Yeah, definitely.
Yeah. That's all. Thank you.
Any more questions on this? Okay. Now let's go to CRTP. So CRTP is nothing but static polymorphism, where you want to have the derived class execute some function. The way in OOPS we do it is have a virtual and then have a virtual in the derived class, have a virtual override and create a object of derived class, point it to a base class and invoke it, as simple as that. So again, we don't want virtual, so CRTP will save. So the base class will have a template type parameter to the derived class, and it will invoke the derived, it will get the derived class from this return static cast and giving it a reference to be saved, constant reference, and it will invoke the do send, do receive. The send and receive will invoke these functions. Now to make the derived class API safe, we have made it private so that only UART can access it. And since we have made it private, we have to make the base class a friend of the derived class. So the API is safe. No one can create UART5 and directly call do send or do receive on. They have to go through the base class. It will by default, they can only use send and receive. In this case, it won't have a base class. So you can always go, this is only two layers, so base and derived. So there can be again, after this, there can be derived two in some cases. But again, it increases the complexity. It's not straightforward to do it, because if you want to derive this derive two from UART5, this itself has to be a template, or otherwise you are deriving again from the base class. So it is again derived one, but at the same level, but a different object. If you want to go and chain this further, then probably as per design, you are not doing any better than OOPS. Again, inheritance comes into picture. So not recommended to do it. So keep it as simple as that. If there is nothing that the UART base class or the base class in CRTP is doing, it is only just forwarding the call to the derived object, then probably use concepts to restrict UART5 to implement do send and do receive directly. There's not even a need to have a base class. But if the derived base class is performing some operation and then passing the remainder of the operation to the derived class, then you would need static polymorphism. So we'll see that in the template method pattern. Now, in this case, when we are using generic programming, probably we won't, just like we did here in SPI, we didn't pass the base class reference as template parameter and pass the object to it. So it is not like a read write peripheral in console, and SPI2 is a reference to that. We directly passed SPI to the object, the type as the object here. So even here, probably I won't create UART reference to a UART5 object. I would directly create a UART5 object. So the way I would do it is, okay, I've not. So in the console, it will be like UART5 and some serial port name. So UART5 says serial port and the object is created. In that case, it is very difficult to know the base class because it does not have a reference to the base class. So to determine the base class of CRTP, and we want to determine the base class because we want to add constraint to it when we are using this object in some function. So to add constraint to it, we would need to determine the base class of the derived object in some form or the other. To do that, suppose we have a string parser and say a command parser, which derives from string parser, a simple CRTP. So this is the base, this is the derived. And I'm creating a command parser as a serial parser. So I'm using this, and I'm using a parse command function, which takes a parser. Now this can take a string parser, command parser, some other parser, pool parser, double parser, or something like that, and do something on it. Now, if I parse in serial parser, parse command, if I parse it serial parser, it does not know that it comes from a string parser. And I want to add a constraint that whatever I pass, whatever type I pass here should come from string parser. So if I use std enable if is base off, and I give the base and the type, there is no way to know it. So this won't work. This constraint would fail. In that case, you'll have to implement specifically for string parser a concept. So the concept will call a function is string parser implementation. So this is a meta function. So this function will take the string parser implementation, this type, and pass it to this, and it will check whether the passed type is the type of the base class. So if I pass a command parser, this command parser, this serial parser will go like this, base like. This command parser goes to base like, and it requires it to be a type of string parser of T. So this command parser is always a string parser of T. So in that case, if I pass a command parser directly to the parse command, this will work fine. This constraint pass. So this concept is calling this, and it is okay. The concept, probably the concept syntax would be a bit new. So this requires will create a copy or reference to the object of this type. So string parser like base like will create a copy of this. So it will create a copy of command parser object reference, not absolute, decal val kind of type, and it will pass it to here string parser. So it goes to string parser, and once it is in string parser, it will check whether command parser is of type string parser T. If yes, it is successful. If no, it will give a compile time error. So adding constraint to CRTP objects, you'll need to know the base class. And that is why I said that using constraints on CRTP is not quite straightforward always. So you need to know the base class, and you can determine the base class using a constraint. Now going to the template method, why are we using CRTP? To alter a part of an algorithm. So this UART will send something, but before sending, it wants to format the message in whatever way. And then the specific UART5, which is our peripheral, will send the message. So in that case, the template method pattern will help you to alter part of an algorithm. So send is a complete algorithm, and let subclasses implement the certain steps. So only the sending part is taken care by the actual peripheral. In these cases, you can use CRTP. If there is no template, then you can probably stick with constraints or direct implementations. So any questions on CRTP or constraints for CRTP as of now. Okay. So let's moving on. So let's go to type eraser. So type eraser is a compound design pattern in which the type information is removed, allowing types that are not necessarily related to be treated in a generic way. So in simple terms, it is a type safe alternative to void pointer. So, and keep in mind that type eraser is always a runtime design pattern. So it will dispatch everything at runtime. The basic type eraser, which we are going to cover, creates the object on the heap at runtime. So that is why the dispatch is also at runtime and it creates a copy. So by definition, type eraser is not a compile time idiom, it is a runtime idiom, but it is a type safe alternative. And it is a combination of bridge, external polymorphism, and in sometimes prototype where you have to clone uh, your object from a reference object. If you don't want to do it, you don't need a prototype. And it will allow loose coupling between unrelated types. So unrelated types in the sense, suppose if I have three tasks and a UI task, a logging task, and a console. As such, these are not related. These are independent services which are being provided. But since we want to run them as a task, we create a base class task and everyone derives from their task. So we don't want to do that. All we want is the task function to be invoked from each of these types at runtime. There is more type eraser can do, but we can achieve this with type eraser. So for type eraser, we will create a task, a structure and aggregate object, you can say, and it has two important details. It will have a concept and it will have a model. This is how the literature on type erasure will define it everywhere. Every type erasure will have a concept and a model. So the concept will define what your object should contain. So any of my task should always contain a run function. That is required, mandatory. And then the model will create an object of that concept and execute it. So when you on the task, when you so in this aggregate object, when you instantiate this object, you can do it with move semantics. Here I've used R value references as well. So here you own the task, you own the object. So it is local ownership. And this is being created at runtime. So since I'm using R value reference, I can forward the object. If I use L value reference, then I need the object to be created and then moved probably if I want ownership of it. I can forward this object. I can create a shared pointer out of this task model, which and of my object. So for example, in this task, I'm going to pass in this task, I'm going to pass in console and LED blink, which are my classes, which I want to run as task. So this console will go here. The task model will create an object of console type. So the type of console is erased. That is why it is called type erasure. Now, internally, I have an object reference to an object of type console. But what I'm operating on is a task model. So the underlying type is erased. I implement or I execute run on task model, which internally calls it on console. And my shared pointer is on the concept. Unfortunately, here we have virtual and it is a base class shared pointer, and we are assigning the derived class task model of the console type. There are some optimizations you can do on it, This is the basic version of type eraser. You can add, since if you don't want to create this, the small buffer optimization is very much applicable here. To some extent, you can add constraints on this, but it gets a bit tricky after some point. If you try to add more, if you try to add some variables, instead of run, you can try to add init, pre-init, post-initialization, a lot of things. So it's not just one function. Then the constraints become quite a bit tricky. So how does this help here is my console, and I have a function called run tasks, which I'm going to call in my main loop, which has a vector of tasks. This task is not the base class of console or LED blink. This is the type erased version. And for this type erased version, I can create a std vector of task, pass the task, my serial console. This is my serial console object, and this is UI object. I can pass it directly. Even for R value, I can pass L value because I'm using straightforward. So it will create a L value reference, and then in that case, I don't own, I have a shared pointer to an object on the stack. In this case, I have a shared pointer to an object on the stack. But you can very well create it inside if you are using a small buffer optimization. And then in this run task, I just iterate over this vector and run. So task run. And if I run this, I will run the serial console and LED task in whichever way. So, and if I want to create a task, this is probably helpful when you want to create tasks on the go, create it, delete it. Probably for when you have some data processing to be done, which changes based on user input. Suppose you have a display and a keyboard, and you have a lot of data processing to be done based on user input. Then probably you might need to do it. There are some other scenarios as well. Yeah, so type eraser, any questions on type eraser?
Yeah. Hi. So just to be clear here, so if we had used the heap, and then we could have saved a lot of this kind of this pattern, right? If
Yes,
heap was not a sensitive application, matlab heap access and heap allocations were not sensitive in this case, then we wouldn't have required to do all of this, right?
right. But if you want to, even if you are doing heap, you can still create these objects on heap and type eraser as well using the same. You can do it. But you cannot, if you don't want to relate this. So if you want to create something on the go and pass it to a task, and if you don't derive it from the task base class, it probably won't have a run function in traditional OOPS
Right.
programming, right?
Right. Exactly.
So if you don't want to link everything through inheritance, type eraser is the one to rescue you.
And what would be the issue if I do link everything to inheritance through inheritance?
That is like a different topic. The Mike Acton will you go through it, because inheritance is something we are trying to get away from in generic programming. Less
Yeah,
inheritance.
that I understand. But
Huh.
in this particular case, suppose you make the console and and each of this you inherit through task, then what kind of trade-off would you face
If
if you have
you
actually?
change tasks, if you change the base class, then or the abstract class, then you'll have to add whatever you add in everywhere.
Right, right.
Probably,
That is absolutely true.
so probably the console or LED blink might not do something which LED blink task might not do something in a way the console will do. So we are trying to relate unrelated things into a base abstract base class in OOPS approach, and then trying to maintain it. Whereas all we need is one function or two functions maximum
Hmm.
to be common between unrelated types. If it is related, then yes, everything will be common, but there is not more stuff common between two unrelated functions or objects.
Right, right.
So that's where type eraser comes into picture.
Right, so we can on the fly we are creating the various kind of objects, and we don't really have to bother about all the bookkeeping for the various types and making sure that they are compliant or not, and all the changes.
Yes, exactly.
Yeah. Yeah. Thank you. Thank you. Thank you for the clarification.
Any more questions on type eraser? Okay, so now we'll go to strategy or policy pattern. So this is very important. So policy-based design, it was introduced by Andre in his famous book. So what he says that you can, the STL uses policy a lot. Policy is something and of an operation for a class. In STL, it is used for allocation or deallocation, which is a policy. So for a vector or for some other container, you always have a policy where you can specify how do you want to allocate or deallocate it, and you want to give us, if you want a custom allocation methodology, say placement new, or you have your own allocation on the stack function, you can provide that as a template parameter, which acts as a policy, allocation policy. So define a family of algorithms, encapsulate each one and make them interchangeable. So allocation, deallocation is one algorithm. There are many ways to do it, and you pass it as a template parameter, as a policy to all your objects. So strategy lets the algorithm vary independently from clients that you use it. So it is not necessarily that allocation, deallocation is specific to a container. It can be, I can pass a allocation policy to my task as well, to a console, to a parser, to anything which is common. So the algorithm remains common. You use it as an external interface or an external API for your object. So, for example, suppose in the logging interface, logging message, we want to log, before logging, we want to format something, format the message, very common. So if I have a format class and it is going to do the process, it is going to format something. So I can log either for the terminal, which can be a VT100, depending on the escape characters and all that kind of stuff, or I can format the same message for file. So we saw I can compress it, I can encrypt it, or I don't want to store it in a string. I might want to convert it into some other format, or I might need to add date, time, something, timestamp for logging, something. So two different ways of formatting. So format becomes an algorithm. And in logging, you pass this algorithm as a type to a template parameter. And in this type, in the private, or private or a local variable, you save a reference to this formatter. So for logging, I can pass, if I have a logger, say logger for terminal. So then logger for, okay, I have not added the example. So logger for terminal will have a format for terminal as a parser, and logger for file logger will have a type format for file. So these will be two different loggers, and uh, it will be pointing or referring to different formatters. And whenever you log, the specific process of that formatter gets invoked. So this still remains common for both the logging. And what if the format class needs to process different types of messages? Now here we are assuming that every formatter will process a character message. What if I want a different type? So this format itself can have a template type parameter, and that type will be the type of the message you want to format. So the strategy can be a template parameter, not a problem. The other approach is this logging client, whichever it is, the terminal or the file, will hold the information of the message type, where uint8, which we are assuming that it is uint8 in both the cases, this type information might be contained in the logging client itself. In that case, the strategy for logging needs to depend on logging itself. So it is a kind of a closed loop. So the logging depends on this strategy, and this strategy depends on logging. Even that is fine, not a problem, because this strategy only needs the information of the message type from logging, nothing else. That is perfectly acceptable. So the important point to note here is the strategy as an algorithm is external to the class, to the logging. We have a reference to the formatter because, and we don't own the formatter, because there might be someone else using the same formatter to log to a file. Very much possible, not necessarily only logging. So we don't want to hold it. We don't want to own it. So strategy is always external. It is reused as an algorithm. Now, in an embedded system, there are so many notifications. So notifications you can consider as a family of algorithms. So in my console, so console will have UART. So UART or the console will notify the terminal. Terminal is the VT100. It will notify the task. UART will notify. So there are so many notifications going on, and there are so many ways of notifying each other. So semaphores, event groups, direct to task notification, mailbox, interprocessor communication. See, all these are notifications, blocking queues, and there can be custom notifications where you have software callbacks and all that kind of stuff. So if you think in terms of strategy, can notifications be considered as a strategy? Because it is a family of algorithms. Now let's see what we can do with it. Now, if we want to notify from UART, which is an interrupt. Okay, so interrupt to task notification. So we can use say direct to task notification in this case, and the console. So UART notification, we can have a function which is again a template function, function template, sorry, which will have a notification source type. So this notification source type is a enum, a simple enum, struct enum, nothing complicated. It will have a task handle, type of task handle, and the actual task handle. Why we are creating a function template is because the uh, direct to task notification API, which we receive from FreeRTOS, has two alternatives. It can either give direct to task notification from ISR or from the app. So these are two different things. So to combine those, depending on the template parameter, we have const exprif in C++17. So before C++17, you might do a function template override, or you can do a tag dispatch, probably a tag dispatch, or std enable if will also work, type traits or a tag dispatch. But C++17 has made it simple. So depending on the source, my source can be an ISR or an app. So if it is an ISR, I invoke this. If it is an app, I invoke this. Now this notification this notification, I'm saving it as a reference, function reference. I can use a std function, state function to hold it, but it is slow because it uses type erasure internally. So std function, if you are using app to app communication, which is not very critical, then probably use std function and pass it. You can pass it a lambda or a function object. That is the beauty of it. But for interrupts, there is not much alternative other than a function pointer or a function reference. So when I create a serial console, so for this function, so I'll create a serial console. I'll create a serial console in the parameter, in the constructor. I will pass this function with ISR because I'm getting from ISR. I'll pass the task handle and I'll pass this console as the task handle. If a task needs to be created first, so the task handle here, okay, for not from embedded, for them, the task handle is a pointer to a structure. So which is always created on the stack. And this is initialized later when you create the task. So this can be null pointer, yes, on the stack. It is how it is. And this console task is created before this assignment is done. Okay. Now, when I want to call back, so in the callback, in the interrupt, how I call it back, UART console callback has higher priority. So it takes a parameter. So we have to pass this parameter. This had nothing to do with uh, strategy or something. This is how the API is. So we can directly call it. Now notice that the strategy here is a function reference, which is external, but this strategy again depends on the console itself, dependency. So it is kind of a loop. It's just that it is not storing it anywhere because it is not an object. So if it was an object, say function objects. So again, direct to task notify, same thing. Same thing, which we have UART notification const expiry that we did in operator this like this. So I've written like this for simplicity. It is a lambda, but like, just to make it clear that this is a function object. If you do it using lambda, you don't have to write all of this. So use a template lambda in production code, but this is just for explanation. So it will have the operator, it will have the same thing, and it will have the notify. And when you can capture the handle of the task and save it here, so it becomes local to your strategy. So the strategy depends on the task handle, and the task handle depends on your strategy, which is very much fine. So you can get other things from here as well. But in all the cases, strategy, if you are using notifications as strategy, you are holding a reference. If it is not a function object, it is a reference. So you are not owning the notification. So similarly, if I have a semaphore notification, so this is direct to task notification, you can have another type of notification. So we replace the type, since we are using strategy, we can replace it with another algorithm. Everything else, the operator, semaphore handle. So instead of task handle, you have a semaphore handle. So you can give a type here and capture it, but everything else remains the same. So it seems like notification can be used as strategy. Awesome. I can have notification as a strategy. Let's see what we can do with it. Now, bridge will go next to bridge. So decouple an abstraction from implementation so that the two can vary independently. Again, coming back to our notify example, see, we have so many notifications. So probably once we send a notification to an LED blink task, which is an observer, this is the subject or the publisher, I would expect a acknowledgement from LED blink. So for the console, it is again an inward notification. If similarly, if it goes this way, again I expect this. So should notification be a strategy or a bridge? So what does bridge do is decouple an abstraction from implementation. Now that does not mean, so LED blink will have a notification inside, which if we have a strategy, it is a reference. Here, note we are not having a reference. We are creating a notify object, which the LED blink object will hold. It owns this notify. And we initialize it in the constructor as well, constructor as it is. And LED blinky notification, how is this an interface? Now, since we want to make it a bridge, this has to be an interface. Decouple an abstraction from implementation. So this we do it with a template parameter. So in the Gang of 4 way of doing it, this will be a reference to a base class. So it will be something called notify pointer mNotify, and this notify pointer will be assigned or an object created here in the constructor, not outside, of type either semaphore notification or direct to task notification or some other, which derives from the notify. So you are holding it and you are decoupling the implementation from the abstract base class. So the same thing we are doing using a template parameter. because we don't want base class and we don't want to create something on the heap. Here you can do std move. There are other things to do here, but we'll just initialize it and create it in a simple way here. So the point is, now, should notification be a strategy or a bridge? Why am I asking this question is because we did use notify in console in LED blink as a strategy, which was a reference to external. And we can use it as a bridge as well, which owns it. So which one is correct or true to use? This is where the line between design patterns is very thin actually, which to use where. That's why I've taken this specific example. Now, if you look at it, even if I'm using direct to task notification for console or UART or LED blink, it is not the same notification. It is the different notification. So each object should own the notification. So UART is going to notify console, but the same notification I'm not going to reuse anywhere else. In fact, I should not reuse anywhere else. So that is why it should not be a strategy. It should be a bridge because I want to own the notification in every case. When we were using a parser, we can reuse it. Probably we can have a queue saying who is using my parsing service. But in notification, the same notification will be sent between two similar objects. There will be multiple notifications, but there won't be one more object using the same notification. So it should be independent and it should be owned. Hence, it should be a bridge. That is the thin line between strategy and bridge. So if you use strategy, if you compare strategy and bridge, see, I have LED blink direct to task notify. This is the bridge version of it. And I use to notify it. How I initialize it is internal to this object. Whereas in strategy, I'm initializing it outside direct to task notification, and I'm passing a reference to the task and then using it. So the internals are visible in strategy, and that is how it should be because it is an independent object or an independent function. But in bridge, it is internal. All we want to say, if you use the old approach, having a pointer to a base class, then probably you won't even need to specify the template parameter here. But in this case, just specify this direct to task notify. Initialization and everything is internal, and you can any external API, the console can just use LED UI.notify, LED control.notify. That's it, done. No internals ever exposed. So yes, that's it. Any questions now?